8.5. Power. The outline of this video is as follows. We will explore the concept of power, which relates work to time. We will define instantaneous and average power, and look at how power relates to force and velocity. Then we will discuss the units of power, specifically the watt and horsepower, and clarify the kilowatt hour. Finally, we will apply these concepts to an example involving an elevator motor. Let us define what power means in physics. Imagine two tasks, where the work done is identical, but one takes significantly longer than the other. While the energy transfer is the same, the rate at which that energy is transferred differs. We define instantaneous power as the time rate of energy transfer, written mathematically as P equals dE over dt. If we look at a specific time interval, the average power is the work W divided by the time interval delta t. Consider lifting a box quickly versus lifting it slowly. The work is the same, but the power required is higher for the faster lift. The essential takeaway is that power measures how quickly work is done. Now we will express power in terms of force and velocity. We start with the limit of average power as time approaches zero, which gives us the derivative dW dt. Recall that infinitesimal work dW is equal to the dot product of force vector F and infinitesimal displacement vector dr. When we substitute this into our power equation, we see that power equals vector F dot product with the derivative dr dt. Since the rate of change of position is velocity, this simplifies to P equals force vector F dot velocity vector v. This equation allows us to calculate the instantaneous power delivered by a force acting on an object moving at a specific velocity. Let us examine the units used to measure power. The standard SI unit is the watt, symbolized by a capital W. 1 watt is defined as 1 joule per second, or in base units, 1 kilogram meter squared per second cubed. In the United States customary system, we often use horsepower, where 1 horsepower equals 746 watts. I must caution you about a common notation confusion. Do not confuse the symbol W for watt with the italicized symbol W used for work. Also remember that since a watt is already a rate of joules per second, the phrase watts per second is physically meaningless. We must clarify a unit that often causes confusion: the kilowatt hour. Despite the name containing the word watt, the kilowatt hour is a unit of energy, not power. It represents the amount of energy transferred in 1 hour at a constant rate of 1 kilowatt. To convert this to standard units, we multiply 1000 joules per second by 3600 seconds, which is the number of seconds in an hour. This calculation tells us that 1 kilowatt hour equals 3.60 times 10 to the power of 6 joules. This is the unit you will see on your electricity bill, as you are paying for the total energy consumed, not just the rate at which you used it. This slide presents figure 8.14, which sets up our example problem regarding an elevator motor. We have an elevator car and passengers with a total combined mass M of 1,800 kilograms. There is a constant friction force F of 4,000 newtons acting against the motion. The motor pulls the elevator upward with a tension force T. We will analyze this system to determine the power the motor must deliver under different motion conditions. We model the elevator as a particle subject to gravity, friction, and the motor's tension. In Part A, we calculate the power required to lift the car at a constant speed of 3.00 meters per second. Because the speed is constant, the acceleration is zero, meaning the system is in equilibrium. According to Newton's second law, the upward tension T minus friction F minus the gravitational force mg must equal zero. Solving for tension, we find that T equals mg plus F. We then use our power formula. P equals tension T times velocity v. Substituting our values for mass, gravity, and friction, we find the motor must deliver 6.49 times 10 to the power of 4 watts. In Part B, we determine the power required when the elevator accelerates upward at 1.0 meters per second squared. Since there is acceleration, the net force is no longer zero. It equals mass times acceleration, ma. Applying Newton's law again, tension T minus friction and gravity equals ma. Solving for T, we get m times the quantity A plus G plus the friction force F. The power is this new tension multiplied by the instantaneous velocity, v. We substitute the values to find an expression for power dependent on v. This demonstrates that accelerating the load requires significantly more power than simply maintaining a constant speed. Let us summarize the key concepts from this lecture. We defined instantaneous power as the derivative of energy with respect to time, dE dt. We derived a useful alternative formula for mechanics, stating that power is the dot product of force and velocity. We established that the SI unit of power is the watt. Finally, we reinforced that the kilowatt-hour is a unit of energy equal to 3.60 times 10 to the power of 6 joules. To close, consider these review questions to test your understanding. First, if two machines perform the identical amount of work, but one completes it in half the time, how does its power output compare to the other? Second, can you articulate exactly why the kilowatt-hour represents energy rather than power? Thinking through these answers will help solidify your grasp of the relationship between work, time, and power.